Thanks for the introduction. So good morning, everyone. So I'm Xiao Chen. I'm a grad student at MIT, but this work was done when all the authors were at NUS. So let's just get started. So today I'm going to first give a brief introduction on speed learning, what's its motivations, and how does it work. Then we are going to focus on the privacy vulnerabilities of it, particularly the privacy vulnerabilities for the client's data. And then we are going to look at some existing attacks and their limitations before proposing our new attacks, which is called SDAR. Then we are going to present our results and discussions, and at last we'll cover some possible countermeasures and point to some future works. Yeah. So some background information. So machine learning has really taken off everywhere in the past decade, but if you really want to train and deploy a machine learning model, you may encounter some bottlenecks. So first, your data is usually distributed over many data owners, and each of them usually only have limited and biased data. And that calls for federated learning, where they can all work together to train a model. And also, sometimes your data owners have very limited computational resources. For example, they can be mobile phones. So that's so those data owners cannot train the machine learning model on themselves. So that calls for machine learning as a service. So both things can be addressed if you just move all the data to a central server that is powerful enough to train the model, but that's compromised privacy. So speed learning, or SL, try to address this problem in a somewhat privacy-preserving way. So the whole idea is that neural networks is consists of layers. And if you have many layers, you can split your layers into two parts. For example, we can put the first S layers as the model F and put that on the client side. And we have the remaining layers, we call it G, put on the server side. And then if the client has features X and the server has the labels of those features Y, then they can work together to train the model. In particular, the client will send the intermediate representations Fx to the server so that the server can complete the forward pass, and the server will send back the gradients of its first layer to the client so that the client can complete the backpropagation via chain rule. Right? So we call this vanilla SL. In this setting, we really need the server to have these labels Y. And a slightly stronger model of this is called a U-shaped speed learning, where the server no longer have the labels Y. Instead, the client has the features and the labels. And in this case, we split the neural network in three parts, F, G, and H. And then the client will have both the first part and the last part. So basically, the client outsources the training of the middle part of the model, which usually majority of the parameters to the server. So both cases, it can work with multiple clients, but today we are going to talk about a malicious server's privacy attack on the client's data X and Y. So in that case, from the server's perspective, its interaction with all the clients would be the same as if they are one virtual client. So we're just going to stick with this model, which looks like one single client. So this is how speed learning works. It protects the privacy of the client's data by sending Fx instead of X directly. So apparently this is a privacy vulnerability because Fx definitely encodes a lot of information about X. And another privacy vulnerability of SL is that the first part of the model F of the client on the client side its update is totally dictated by the server's gradients that is sent back. So by exploiting these two vulnerabilities, existing works have shown that a server is able to reconstruct the features and sometimes also labels of the client to a certain degree. However, some existing server-side attacks, they may assume a particular strong assumption for the server. For example, sometimes they assume the server is active, which means that it sends malicious updates back to the client that might be detectable. Or sometimes they assume that the server has access to the client's model. Which is not feasible, as you can see here previously. The model lives on the client side. You shouldn't have the access to that. So and also some existing server-side attacks targets easily exploitable models that are easier to attack, and their performance will be much worse if we test that on more challenging settings. So our paper considers the same threat model as the current SOTA passive attack PCAT. In particular, we consider a passive setting where the server is honest but curious. It never tampers with SL protocol. It always sends honest messages to remain stealthy and undetectable. And also, we require no access to the client's model, whether it's white box or black box. And our attack can attack both the client's features and labels if in the U-shaped setting, with better performance than PCAT and the challenging settings. And the only thing we require for the server to have is a labeled auxiliary data set that is in the same domain as the client's data sets. This is also the same assumption for PCAT. Yeah. So now that we assume this labeled auxiliary dataset, there is one particularly naive approach to attack, which is that the server can train a simulator model tutor F on its side such that together with G, tutor F and G can classify X prime to Y prime, which is the auxiliary dataset. And this is just like training in a normal supervised learning way. And then because this tutor F is like a white box to the server, you can train a decoder of that model as well. So the hope is that if tutor F can learn something together with G, probably is behaving similar to what client has on its side, which is F, then its decoder can also decode F. But that's not the case, if you can see here, right? The reconstruction results are really bad. And there are two reasons for why this naive approach doesn't work. First, the simulator tutor F can classify X prime together with G, doesn't mean that it has learned the same representations as the client's private model F. And also, the decoder can decode this simulator doesn't mean that it can decode the client's hidden model F. Right. So we try to solve these two problems separately, but with the same methodology. So the first issue is that we want this simulator F to learn the same representations as F, not just to be able to classify together with G. So, however, we don't have access to the client's model F. What the server does have is a bunch of intermediate representations fx it observes over the time during training. So we can introduce a discriminator, we call it D1 here, to distinguish the output of f and the output of tutor f. And then we can add a GAN generator loss as a regularization term when we train the simulator tutor f, so that it is trained to optimize, it is optimized to produce representations that look similarly to the client's output fx, at least to the discriminator. So the next issue is that the decoder can perfectly decode its own white box simulator tutor f, but when we use that decoder on the intermediate representation we receive, the reconstruction look like this. So apparently it doesn't look like real images. And recall that our server has access to real images, which is X prime. So we can introduce another discriminator D2 that try to distinguish the real images X prime and the reconstructions on the client of the client data. And then again, we can add a generator loss as a regularization term when we train this decoder, so that the decoder will be trained to minimize the to reconstruct plausible images when it's try to decode the client's private images. So together, these two things we call them adversarial regularization because it's like GAN style stuff, and we use that as a regularization term in addition to the original like simulator training. So we call this thing a simulator decoding with adversarial regularization, or in short, SDAR. Our paper also includes some other techniques we use it in the attack, but I'm not going to like go into the details of that. So now let's look at how SDAR works on vanilla SL. So you can see here, our attack have a much lower mean squared reconstruction error on the vanilla setting. And you can see with steeper split levels, which means that more layers is assigned to the client rather than the server, it gets harder to attack. But in other cases, our attack results are better. And more visually speaking, you can see here that when we increase the speed levels, our attacks still remain effective, while PCAT struggles to produce meaningful reconstructions when speed level is too high. So particularly here, when speed level is 7, basically half of the model is on the client side. Yeah, and in particular, our attack results almost match the attack result of FSHA, which is the state-of-the-art active attack, where the server actively modifies the messages sent back, and literature has shown that that is detectable. Yeah, so now that's about vanilla SL. So what about the U-shaped SL? So for U-shaped SL, the server no longer has client's training examples, labels, or the final layers of the model. So now we really try to attack both things. We need to attack X, and we need to attack Y. So we have the same idea. We have this auxiliary dataset X prime, Y prime, so we still need to train a simulator model, right? So now we need two simulators. Because we don't have F, we don't have H, so the server will have to introduce the simulator tutor F and the simulator tutor H, so that this tutor F, G, tutor H thing can classify X prime to Y prime. And again, if the simulator works just like what clients had, then you can decode tutor F. Then if you have a decoder that can decode tutor F, we hope that it can also decode F. Okay. So just like the vanilla attack, we still need to like make sure the tutor F and its decoder will generalize well to the private data that is unseen by the server. So we still have these two discriminators, we still have the adversarial regularization techniques. But the question now is that how can we make sure the same thing happens to tutor H, where tutor H will not learn like two specific mappings for x prime, y prime. So we apply random label flipping on the y prime labels when we train tutor H, so that it will learn the general representation that will work with G, rather than like overfit to x prime, y prime. And it turns out this thing is also useful when we do label inference attack. We just need to feed the GFX to tutor H, and if tutor H is really working well and behave like H, then that is a valid reconstruction of the labels. And here are our inference, feature inference attack on U-shaped SL. You can see that, again, our reconstructions are much better. And here we see that PCAT really dropped its performance on the U-shaped setting, but ours really don't. That means that our tutor H is really doing a very good job mimicking whatever H is doing, so as if H is never gone. So you can see here are some examples of the reconstructions, and the performance gap is even larger. And for label inference results, you can see here are the results for PCAT, and here is our results. You can see across all the speed levels, we achieve very good label inference accuracy. So in our paper, we also discussed some other things. We look at the effects of auxiliary data distribution or target model architecture and the effects of server's knowledge of the client's model architecture. And we also do some ablation studies. You can check out the paper for the details. So in the end, I want to talk about some potential countermeasures. So first, we try like assign even more layers to the client. So in one extreme case where we assign all the layers but the last layer to the client, so this is very extreme and that totally defeats the purpose of SL, and that is very challenging, but our attack is still workable. Another thing I want to mention is the third thing, which is the decorrelation defense, where the attack can minimize the distance correlation between its input and output, and even under that decorrelation defense, our attack remains effective. So we can also try some cryptographic protocols, but that will include too much computational overhead and defeat the purpose of SL. We cannot do differential privacy here because we are sending FX, which is not aggregated information. So that's all for the talk, and I'm happy to take any questions.
Thank you so much. Thank the speaker. Questions? Have time for questions, please.
Thank you. How much dependent is your attack on the auxiliary data? Did you test it without auxiliary data?
It has to have some auxiliary data. We've tried that when the data is when it has a very, when we have a very small data set, it still works. We try that when our data sets do not have like 10% of the labels of the classes, it also works. So that is like when I say the effects of the, the effects of the data distribution on our attacks.
Okay. And you showed that you, as all the attacks, tested on image dataset, but did you test on other domain dataset?
No, we just test on, we test on Cypher 10, Cypher 100, we also test on larger images.
Yeah, images, yeah. Okay, no text or other.
Super, more questions.
Thanks for talk. So I have a question about your client setting. How many clients you consider? Just one client, one server setting?
Yeah, because like if the clients all have the same data distribution, so it's almost like all the clients are doing the same thing. So it's like a virtual larger client, right? And we also try with, so it only makes sense to talk about multiple clients if the clients have different distributions. So we also try with heterogeneous clients, and I think we have a dozen of clients. I don't remember this like accurately, but we have that result in the paper. Yeah.
And the following question is about, so for your presentation, I understand you talk about the classification task, like supervised learning. So have you considered using the, for example, contrast learning, this kind of different setting?
Oh yeah, we didn't consider that, but that seems like an interesting approach where we want to learn like similar representations, and yeah, I think that may be effective. Yeah, thanks for the question. Yeah.
Very good. Maybe I take one last question. Yeah. So countermeasure summary for me is your attack cannot be defeated easily.
Yeah, not with
that's from your slides, but I cannot believe this. There must be something that we can do to thwart your reasoning, at least.
Yeah, I think that with some like there are some defense we didn't try. For example, we can add noise. I think if we add noise, then it will be able to like.
Noise where? Where would you add it?
Add noise to FX.
Okay.
Yeah, that's one possible thing. we can do, because like noise cannot be easily learned.
Yeah.
But all the three things I mentioned that cannot defeat our attack, they are quite learning-based. So if it's learning-based, I guess is that our attack will still work. Yeah.
Very good. Okay, then let's thank the speaker once again.
Yes, thank you.